Welcome to this video lecture on the subject electronic circuits. So in this we are going to discuss about collector to base bias method. So in the previous lecture we have discussed the fixed bias and emitter bias circuits. So in this lecture we focus on collector to base bias. So as shown in this diagram, another way to improve the stability of the base circuit to add a feedback path from collector to base. So consider the diagram where in the collector terminal RC is connected to the power supply, and also we take the feedback such as resistance RB is connected to base. So this acts as the feedback path. So in this bias circuit the Q point is only slightly dependent on the transistor beta, so that we can get the stable current. So for analyzing this collector to base bias circuit, we need to apply Kirchhoff's voltage law. So for the base emitter loop, we consider applying KVL as VCC minus IC into RC. So through the feedback path, there is an resistance RB. So minus IB into RB minus VBE minus IE into RE equal to 0. So from this condition, we get applying the condition IB less than or IC, which is equal to IC plus IB. So by substituting the IC values, the loop equation becomes VCC minus beta IB RC. So minus IB into RB minus VBE minus beta into IB RE equal to 0. So we can solve for the base current from this equation. And applying the KVL for the collector emitter loop, we have IE into RE plus VCE plus IC into RC minus VCC equal to 0. So from this equation we obtained VCE value, and also we have substituted IE equal to IC, because here the emitter current is approximately equal to collector current. So we get a collector emitter voltage as VCC minus IC into RC plus RE. And also base emitter bias analysis. Here the transistor saturation level is calculated, that is the saturation collector current, it is equal to maximum collector current, which is given by VCC divided by RC plus RE. So load line analysis, we take the cutoff region and saturation region. By substituting the value of VCE and IC, we get VCE equal to VCC and IC equal to 0. Similarly, IC equal to VCC by RC plus RE and VC equal to 0. So this values gives the load line. So from the analysis we can calculate the stability of the transistor. So bias stabilization, the stability of a system is a measure of the sensitivity of a network to variations in the parameters. So in any amplifier employing a transistor, the collector current is sensitive to each of the following parameters. First one is beta, the increase with increase in temperature, and VBE, that is base emitter voltage, decrease about 2.5 millivolt per degree Celsius, increase in temperature. So these are the changes of the values according to the temperature. And reverse saturation current, it doubles in value for every 10 degree rise in temperature. So when these values changes, it affects the stability of the transistor circuit. So you go for bias stabilization methods. So it depends on the stability factor. So better bias circuit, it will stabilize the collector current and maintain the DC bias. So the stability factors are given as ratio of collector current to collector saturation current, and also ratio of collector current to base emitter voltage, and ratio of collector current to beta. So the networks that are stable and relatively insensitive to temperature variations have low stability factors. So higher stability factor means it is more sensitive to variation of parameter. So let's take the assessment, discuss the advantages of collector to base bias circuit. So we have initially discussed the limitations of a collector base bias circuit and also the advantages. So here the advantages of the circuits is it is very simple in construction, and also it needs only one resistor in the feedback path. and the circuit provides some stabilization for lesser changes in the parameters of a transistor like beta uh, and also the base emitter voltage. So when we consider stabilizing the bias circuit, we will add a diode circuit or a thermistor or sensor circuit that we will discuss in the next lecture.